Hello, we're going to look at increasing and decreasing functions today. So when we're trying to decide whether a function is increasing or decreasing or a bit of both, we're going to need to consider the first derivative. So this is dy by dx and it represents the rate of change of y with respect to x. So we're going to start off by thinking about some simple examples. The easiest examples to demonstrate this would be a straight line. So if we consider a straight line that has gradient 3, so this could be something like y equals 3x plus 2, we would say that dy by dx is 3, and because it's positive, that means for every increase in one of x, then you're going to increase y by 3. So we can see that as we go along the x-axis, as we increase our x values, our y values will most definitely be also increasing. If we then consider a straight line with a negative gradient, so for example y equals minus 4x minus 10, then our dy by dx value, our gradient function, is just a negative 4, which we know means that as you increase x, the y value is going to decrease, because that represents every 1 you increase in the x direction, you decrease by 4 in the y direction. So we already fully understand that positive gradients result in lines that go up and negative gradients result in lines that go down. But now we need to make sure that we can translate this over to curves. So we're going to consider a quadratic, so let's just consider y equals x squared, and we know that this is a graph that goes down and then up again, so it definitely isn't just increasing or decreasing all the way across it. So if we take y equals x squared and we differentiate to get our gradient function, we're going to get 2x. So what's happening here this time is we don't have a constant gradient. Okay, unlike a straight line, we can't say for definite whether 2x is positive or negative if we're not going to restrict the values of x. So we have to consider how dy by dx changes as x changes. So when is this gradient function positive? Well, that happens when x is positive. So for this particular example, for all positive values of x, you will also get a positive gradient. If we do the same, if we consider, well, when is this gradient negative, then it's when x is negative. So we have particular values of x that determine when this function is increasing or decreasing. And that's what we're really looking at here. We're looking to see whether the gradient function is positive or negative. So let's just look at the graph so that we can make links here. Okay, so we've by looking at the gradient function 2x, we've decided that the gradient would be positive when x is positive. So if you look at from x going 0 in the increasing direction, the curve does indeed go up. So the curve is increasing for all positive values of x, it's always going up. And then as you go into the negative x values and you get more and more negative, the curve is decreasing. So as you move up in the x values, the curve is going down. Okay, so this is a good example of a curve that goes from decreasing to increasing, and we know that the point right in the middle, exactly where the gradient equals 0, that would be our turning point where the graph changes from being decreasing to increasing. So let's make a note of our standard result then. And I've chosen to write this one in function form because it's just so much nicer than writing dy by dx. Remember, the dy by dx and f dash of x mean exactly the same thing. It means the first derivative of the function. So we have got that if a function is increasing where the second derivative is greater than or equal to 0, and decreasing where, the first derivative is less than or equal to 0. So you might get questions where you have to show that curves are increasing or decreasing, or you might have to find the range of values for which a curve is increasing or decreasing. And we'll look at a couple of examples in just a moment. There's one more thing to note about this. You might be thinking, but why we equal 0 for both increasing and decreasing? Surely it's just greater than 0 and less than 0. And yes, if it is just greater than 0 or less than 0, then we actually say that it's strictly increasing or decreasing. But if you consider something like y equals x cubed, that's the curve that comes up from the bottom left, it goes slightly flat and then it carries on going up. That curve is increasing for all values of x, but it does have a point where the curve goes flat. So it has that point of inflection. So we would still say it's increasing for all values, rather than it's increasing until you get to x equals 0 and then increasing again after x equals 0. So we include 0 when we're just saying increasing or decreasing. If we want to say strictly increasing or decreasing, that's when we would have our strict inequality. Okay, let's do an example. Okay, so we're going to be finding the set of values for which this function is increasing. So we're looking at solving the first derivative. So we're going to find the first derivative, and we're looking at for when setting that to be greater than or equal to 0, positive gradient. So I'm going to call this f of x so that I can just say f dash of x and not worry about writing dy by dx out. So we go through and differentiate this. So bring the power down, times by the power, take 1 from the power. So we're going to end up with 2/3 times 3 is just 2. So 2x squared. Do the same thing here. 9/2 times 2 is 9. And then we just get -5 from that term, and the 3 differentiates to 0. So we're looking for when it's increasing, which means we're looking for when this is greater than or equal to 0. Now, for solving a quadratic inequality, firstly we're going to want to find the roots of the quadratic, because they're going to be the values that are when the function equals 0, and therefore it will be either in between those two values or outside of those two values that we'll be interested in for when it's greater than or equal to 0. So this can actually be factorized. So now we're going to have 2x and x at the front of our brackets. We're going to need a 5 and a 1 with opposite signs to make the -5. So if we want to make 10, so we're going to have the 5 over here. So we get 5 times 2 is 10x. And then we'll take away 1x, so we'll make that minus, make that plus. There we go, that works. So if we just get the solutions, we're going to have x is a half and x is -5. Now I always strongly recommend that you do a little sketch of your quadratics when you're solving quadratic inequalities in particular. So we're going to have -5.5, so it's going to cut through there and over here. -5 doesn't have to be anything fancy, you're not going to get marks for it or anything. It's just to help you make sure that you get the right right set of values. So the question is, are we going in between them or are we going outside of them? We want when we're greater than or equal to 0, and this gradient function is positive, so we want the bits that are above the x-axis, and that's going to happen when we are less than -5 and when we are greater than a half. Now we could write this as an inequality as our answer, that would be absolutely fine, but I figured I'd take the opportunity to just show you a different way of stating a range of values using brackets, which is going to look a bit strange if you've not seen these before. We can actually use either normal curved brackets or the kind of straight square ones to define a range of values. And because we are or equal to 0, then we're actually going to want to use the square ones. So we're going to start off by doing our left square bracket, and we're going to write this a bit like a coordinate. We start off with our lower bound, so this is what we're on the lower end of. So if I'm doing the range of values that are below -5, I'm actually going to put -infinity because there is no bound on the lower end. And then my upper bound is -5, so I would write that range there is basically me saying, this is the same as me saying x is less than or equal to -5. It's just a different way. You might see this notation, so it's good to know what it means. And then the other parts is that or above a half, so half would be my lower bound, and then infinity would be my upper bound. So this is like saying x is greater than or equal to a half. Now I do not want to combine these inequalities in any way because they are two separate ranges of values. They do not overlap in any way, so there's no need to try and write them as a single inequality. In fact, it would be wrong to write them as a single inequality. Okay, so that these are the values of x that would give me increasing, so give me where the curve is going up on this cubic. All right, we'll do one more example. All right, this time we're actually going to be showing that a function is decreasing for all values of x. So rather than having a bit where it's going up and a bit where it's going down, it's just going to be going down the whole time, and that's what we're hoping to show. So I'm going to do the same thing again. I'm going to call this f of x so that I can write my first derivative as f dash. Now, before I actually go ahead and differentiate this, I've noticed that I've got some brackets going on here, so I'm going to want to expand them. So just above the function, I'm going to rewrite this function fully expanded. So -2x times 3 is 6x. And then -2x times 5x squared is -10x cubed. So let's go through and differentiate. So the 10 differentiates to 0, then I'm just going to get a minus 6 from the minus 6x. And bring the 3 down, I'm going to get minus 30x squared. And I want to show that this is decreasing for all values of x. So what I'm aiming for is to be able to say with confidence that f dash of x is less than or equal to 0, no matter what value of x I put in. Now if I consider what I've got here, negative 6 is a negative number. X squared is the only bit that depends on x, but x squared will always be positive, right, because it's a square number. So I'm going to start with that. So as x squared is positive, this means that if I factorize the negative out to make this a bit clearer, so that's actually going to be 6 plus 30x squared if I take the negative out. So then I can say that 6 plus 30x squared, or actually I can say here that this is greater than or equal to 0, because you can put 0 into x squared. But it does mean though that if I then times it by 30 and add 6, that I am now strictly greater than 0. So this bit in the bracket is most definitely always positive for all values of x. And then I can just state that this must mean, so I'm going to do my therefore dots, minus this thing that I've just said is always positive, must be always negative. So that means that my gradient function, so this implies that we actually upgrade what the question said, and we can say that this is strictly decreasing for all values of x. Now actually I'm going to show you a little bit of notation. Rather than writing for all, we can actually do this upside down a that means for all values of x. Not something you have to use, but it is a nice little way to be a bit lazy and not write so much, which is what generally mathematicians like to do. Okay, so there we go, we've got 2 examples. I hope you found that helpful, and if you did, I'd appreciate a like. Please subscribe to the channel if you want to see more, and I will see you in the next one. Bye.